Greetings of the day everyone. This is second video in the lecture series of revision of basics in Boolean logic. The subject is computer organization and architecture with subject code CB302. It is basically targeted for CSBS branch third semester. Let us start with the concept. Logic gates. For electronic circuit or digital circuit, the basic component is logic gate. Basically, it is electronic circuit in which electrical signals are passed. So electrical signals may be concerned with voltage or we can say with current. So these logic gate or digital circuit, we say in general language that they operate on values 1 and 0. So basically what 1 stands for and basically what 0 stands for is that if the voltage is 0 volt or near to 0 volt, then we consider the state of the logic gate or any digital circuit as level 0. Whereas if the voltage value is 3 volt or near to 3 volt, then we will say that the circuit is on value high or value 1. This diagram very accurately represents that how the voltage on the output of the logic gate or any digital circuit is considered. See, on the y-axis, we can see that if the voltage level is from 0 to 1, then the signal is considered to be logic 0. Whereas if the signal level is from 2 to 3 volt, then the signal is considered to be at logic 1. So digital logic gate. What is a digital logic gate? Digital logic gate, it is made of, you can see 3 words. Digital, that means the circuits, the thing which we are going to consider is considering the digital signal, that is in the form of 0 and 1. Then second word here is logic, that there is some logic, some condition. If that condition is fulfilled, then the output would be high or low according to the logic. Then gates. So the work which is performed by these circuits, we can compare it with the gates. A very good example of this. Consider your house gate. So if anybody comes there, if that person is known, this is the condition, whether the person is known or not. If the person is known, that means your logic is true, then you will open the door and the person can enter into the house. That means the logic is true. So you have passed the signal. On the output you will get high. Whereas if the logic is not true, that is the person is not known, then you won't open the door and the person cannot enter into the house. So in logic gate circuit, if the condition is not true, not fulfilled, then on the output we will get 0. So these logic gates are basically categorized in these 3 mentioned classes. The first one is basic logic gate. They are the most, you can say, the oldest logic gates. The example of these gates are AND gate, OR gate and NOT gate. The second category is universal logic gate. Universal logic gates examples are NAND and NOR. We call them universal logic gate because by using only NAND or only NOR, you can design all other basic logic gates. And with basic logic gate, as we know that we can design any digital circuit. So what implies now that using the only NAND or only NOR, we can design any digital circuit or any digital logic gate. That is why these are called universal logic gate. The third class of logic gate is exclusive logic gate. Exclusive logic gate, they are giving you high output when any condition is exclusively true for given inputs. The examples are XOR and XNOR. So what are the conditions? We will see in the next slide. Here we can see the logic symbol and truth table of all the basic and universal as well as exclusive logic gate. First, see the symbol. We call it logic symbol of AND gate. Here two inputs A and B are given and Y1 is the output. We are considering the smallest gates here. Smallest means, as we have shown, only two inputs there in AND gate, but there are two or more than two inputs are possible in these logic gate except NOT gate. NOT gate only have single input. So AND gate is having two or more than two inputs and only single output. If you observe the truth table, you will understand that output is high only when all the applied inputs are high. Otherwise, if one or more than one inputs are 0, then output is 0 for AND gate. Whereas, if you see in the OR gate, the logic says that if one or more than one inputs are high, then the output would be high. Otherwise, if all the inputs are 0, then output would be 0. Now the third gate is NOT gate. It is also called complement gate or inverter gate. It complements the input. Remember that in NOT gate we have single input possible only. So if that single input is 0, the output would be 1. If the single input is 1, the output would be 0. Now comes the NAND gate. If you observe the logic symbol, you can see that it is NAND gate followed by an inverter. So whatever output we are getting in the truth table of AND gate, the NAND gate provides the complement of that. So for 1 1 value, when all the inputs are high, then only output is 0. Otherwise, in all other cases, output is 1. NOR gate. NOR gate is OR gate followed by a inverter. So its output is complement of OR gate. So when all the inputs are 0, then only you will get 1 at the output. Otherwise, in all other cases, you will get 0. XOR gate. See, in XOR gate, when the input is applied, the condition is that exclusively odd number of input should be high, or if we are considering two inputs here, then only one input should be high. Then only output would be high. Otherwise, in all other cases, if even number of inputs are high or no input is high, then output would be 0. So for 0, 0 and 1, 1, we are getting 0 at the output, and for 1, 0 and 0, 1, we are getting 1 at the output. XNOR gate, if you compare the logic symbol of XOR and XNOR, you will see there is one inverter or NOT gate at the output of XOR gate. So whatever output we are getting at the output of XOR gate, its complement is there in the XNOR. So here, when even number of inputs are high or no input is high, then only output is high. Otherwise, in all other cases, when odd number of inputs are high, the output would be 0 only. So for 0, 0 and 1, 1, we are getting 1. For 1, 1, we are getting, see, observe the difference between XOR and XNOR. For 1, 1, in XOR we were getting 0. For XNOR, for 1, 1, we are getting 1. So it is complement of each other. This is how we generally represent the input-output signals for logic gates, even for other digital circuits also. For representing 0, we represent a low level line, and for representing high value or 1 value, we are representing the upper level of signal. When our input is 0, 0, corresponding AND gate, OR gate and NOT gate outputs are shown. These are 0, 0 and 1. For 1, 0 inputs, we are getting 0 at AND gate, 1 at OR gate, 0 at NOT gate. Similarly, for 1, 1, AND gate provides 1, OR gate provides 1 and NOT gate provides 0. Then for 0, 1 input, the AND gate provides 0 as the output, OR gate provides 1 and NOT gate provides 1. Likewise, we can represent the waveforms, that is input and output signals, for all other logic gates, that is NAND gate, NOR gate, XOR and XNOR, or any digital circuit. As we have already discussed that except NOT gate, all other logic gates are multiple input. That is, there are 2 or more than 2 inputs possible. So this diagram shows that how 3 inputs are applied to AND gate, ABC are applied to AND gate, and the output F is multiplication or AND of A, B and C input signals. Whereas a 4 input OR gate is also shown here. Here inputs signals are A, B and C, D, and the output is generated on the basis of OR operation between inputs A, B and C, D. The output is named as G. Likewise, we can represent the multiple inputs for all the logic gates except NOT gate. So happy learning, students. We will meet again in the third video of this lecture series. Thank you.